Actually, there is some connection issue, so I'm just resolving it. Yeah, just wait for some seconds. There is some connection issue. I'm just so yeah. I think the screen is visible. So there may be some connection issues today. So I'll try to manage, but we'll see uh, how it goes. So yeah, so today we will be discussing about week 5 lecture sessions, whatever professor told about us. Before that, we will just go through what we studied in week 4 lessons. So in week 4, we talked about comparators. Uh, yeah. So we talked about in week 4 we talked about comparators, window detectors, and then we saw the working of window detectors, how they work. Then we talked about op-amp comparators with positive feedback and why we need them because of noise and all. So then we talked about Smith triggers with one reference voltage and two reference voltage, and why we introduced two reference voltages in Smith trigger. Then we talked about inverting Smith trigger and its working, the non-inverting Smith triggers also. Then, yeah, we also talked about what is hysteresis width and voltages, and we talked about the voltage transfer characteristics. And then we discussed the assignment questions as well as some extra questions previous week. So this week, as we are um, talking about the non-linear applications of the op-amp, so today we will be looking into non-linear applications of op-amp. So why we are saying it non-linear? Because in every application we are using the positive feedback, not only the negative feedback. So earlier we talked about comparators, then we talked about window detectors, then we talked about now we will then yeah we also talked about Smith triggers. So today we will talk about astable multivibrators, multivibrators, and we will also talk about monostable multivibrators. Okay, so and then we'll also these are all non-linear with positive feedback, non-linear application of op-amps with positive feedback. So today we'll start with stable multivibrators. That is the first topic. which we saw in the week 5 lecture. Stable multivibrators. Okay. So as we know, so these kind of op amps use positive feedback, uh, and then but why we say them as stable multivibrators, because this thing, it is having both states, like positive and negative, that is high state and low state, but both are unstable. So it will not be stable at one particular stage, it will keep on changing, either positive or negative, like that. So then, if we see the circuit of this stable multivibrator, so we know that in this, if we just change this thing, plus this is minus. So we saw in Smith triggers, we had a positive feedback like this. So let's say this one is R2, this one is R3, and this is output voltage, and this much this much part we saw in the Smith triggers. But in this circuit, in stable multivibrators, we have attached one capacitor and a resistor in negative feedback. So how it will work? So as we know, since this is stable, so it will keep on changing. So output pulse will be like this: plus V saturation and then negative V saturation. Okay, and the frequency of this, if this is given by 1 by 2 pi RC. So since we have added RC circuit, so we'll see the functioning of how this RC, this stable multivibrator will work like. So, uh, but before that, if we talk about its application, so this five multivibrator can be used in pulse position modulation and frequency modulation also. Okay, now we will see how uh, this will work. Right. So if we see the circuit, so first will think how Smith triggers work. So Smith triggers works. So if we talked about Smith trigger circuit, let's say this was a Smith trigger circuit. If I'm talking about inverting Smith trigger, so it was like this. Okay, this one was R1, this one was R2, this one was V naught. So when we were applying something, so based on this, let's say this is VB voltage, this is VA voltage. That VB voltage is at the non-inverting side of the op amp, and VA is at the inverting side. Sorry, VB at the non-inverting side of the op amp, and VA at the non-inverting side of the op amp. So based on the magnitude of VA and VB, we were deciding what will be V naught. So V naught will be either plus V set. It is that when VB is less than VA, and it can be minus Vset when it is when VB is greater than VA. Okay, so this we saw in Smith triggers, but now in this, how we will approach the circuit, the functioning is same, but only thing what we changed here is that we added one capacitor here. So since we know how the capacitor works, so capacitor is based on charging and discharging, based on the input given to it. So same thing we will see here. So since we can see here, there is a RC circuit here. So we will see the functionality of RC circuit in this op amp application. Yeah. So so we'll start at, so first step, like we'll start at t equals to 0. So we'll see. We are assuming initial voltage for for convenience. I will make the circuit here. This is plus, this is minus. Uh, okay, this is, So I'm making the stable multivibrator circuit here, so that we can simultaneously look at the circuit also. R, C, this is C. Okay, grounded. Fine. This we can say R2 or R3. This is R2. Now at t equals to 0. So we are assuming that initially the voltage, wait, just, yeah, the voltage across capacitor, we are assuming it to be 0, is 0. Fine. This capacitor is having no voltage. So after that, and also the output is at plus Vsat. Let's just for assumption we are saying the output is at plus Vsat. So what will happen? So this output is at plus Vsat. So this voltage is being fed back to capacitor. So capacitor is like from the, oh sorry, this is plus, this is negative. So capacitor is being charged with this positive Vsat. So what will happen? How the waveform will look like? So two. So initially, or yeah, so initially we can say this was at 0 capacitor voltage, so it will charge, it will start charging, capacitor will start charging. This is capacitor voltage, this is output of op amp. So we are saying here the output of the op amp is plus Vsat. So based on, because of that, the capacitor is charging. So here it is charging. Okay, so then what will happen? So it will charge till certain limit. So that limit will be decided by this voltage. So since we are having plus Vsat, so the feedback, the positive feedback given at this point, what it will be? It will be beta Vsat. Okay, so this voltage is being fed back via the positive feedback at the non-inverting side of the op amp. So that voltage is plus beta Vsat. So based on that, once the voltage, see the capacitor voltage, which we can say VA here at this point, and let's say at the non-inverting side we can mark it at VB. So once this VA becomes more than VB, once it become more than VA becomes more than VB, then what will happen? The output of the op amp will switch its position from plus Vset to minus Vset. Okay. So then what will happen? Since output of the op amp was plus Vset, once it reaches plus beta Vset, the charging of the charge of the capacitor, then this output of the op amp will change its direction and it will become minus V saturation. Fine. So once it becomes minus V saturation, what will happen? Then this voltage, instead of beta V set, it will become minus beta V set. One thing. Okay. Next thing, what will happen? Since this is now minus V set, now the capacitor which was being charged till beta V set value, now it will, since the polarity will be like this initially, now the polarity of the capacitor will start changing, or we can say this capacitor will start discharging through this RC network. Okay, because we are now providing negative voltage to the capacitor, so it will start discharging. Okay, so it will uh, come to a certain limit. So this limit is again the limit being decided by the VB voltage, that is, now it is minus beta Vset. So once it achieves minus beta Vset value, the capacitor, then again what will happen? This VB, so it is now tending to go even less than minus beta Vset. So what will happen? VA, now instead of this, it will become VA will be more than VB. VA will be less than VB. So what will happen? The op amp will again switch its position. So it will change again to plus minus Vset to plus Vset, and this keep on changing. So we will get a waveform like this. So this is negative, the plus beta V saturation, then again this, then this. It will keep on charging, discharging. So what we got? So we got an unstable multivibrator Why? Because it is keep on changing from high state to low state. Okay. Here, what is the beta factor? Beta factor is R2 upon R2 plus R3. Okay, because we have R2 is this resistance and this R3 is the resistance joining the output voltage and the non-inverting terminal of the op amp. Now, so now we also know that the time period of this circuit is t equals to 2 RC ln 1 plus beta upon 1 minus beta. But how we achieve this? So we'll see that also. So how we achieve this voltage? Okay. So we know one equation of capacitor voltage, that is, so we basically now we need the, this is the charging and discharging total time. So total time, we can say this is total time. This is discharging time TD. This is charging time TC. Fine. So if we just talk about TD, the discharging time. So let's say we have to derive this thing. Okay. So how we'll achieve this equation? So we'll see discharging time. Discharging time, that is TD. Okay, so we know one equation, the voltage equation for a capacitor, that is the voltage across capacitor is equals to the final voltage of the capacitor plus V final minus V initial voltage across capacitor into e to the power minus t by RC. So now if we are talking about this only this state. So here initial voltage is plus beta V set. Final voltage, it needs to go till what? The capacitor needs to attain the negative V set value. So this is like, let's say we can say minus V set. So it wanted to achieve minus V set, but before that I start charging again because of the reference voltage set by the positive feedback of the op amp. So we can say the V final voltage which capacitor wanted to achieve was minus V set. Okay, and the initial voltage it was having was plus beta V set. Fine. And since we have to calculate till this point, so this point the VC voltage is what? VC is equals to minus beta V set. Okay, so again we'll see. So final voltage the capacitor what wanted to achieve, so that was minus beta V minus V set, and the initial voltage what it is having right now is at this junction is this point. So it is like plus beta V set, and the voltage which is being achieved by the capacitor is what? Minus beta V set. So putting these all values in the above equation, we can get minus beta V set equals to V final is minus V set plus minus V saturation final voltage minus beta V saturation e to the power minus TD by RC. Okay, this is the discharging time. So what will happen if we can just cut? I'll just solve this. Minus this will be plus beta 1 plus V sat 1 plus beta e to the power minus TD by RC. So this will be beta minus 1 divided by 1 plus beta equals to e to the power minus TD by RC. Now if we take log on both the sides, we can get minus TD by RC equals to beta minus 1 ln 1 plus beta. So TD will be what? It will be RC ln 1 plus beta divided by 1, yeah, beta minus 1. Okay, I think, oh, I think some connection issue again. Is it? Hmm. Oh, oh yeah, yeah. Yeah, I think some connection issues are there, so sorry for that. So yeah, now I think it is fine. uh, so we achieved this value. So it is, yeah, so beta minus 1. So this is T discharging. So if you see, uh, so similarly what we can do for the charging time for TC, that is charging time. Okay, charging time, that is the time between this point, these two positions. So here again, if we just know what is the V, this again, if we see this equation, Vc equals to V final plus V final, uh, V final minus V initial into e to the power minus t by RC. So V final, what will be V final here? If we now, if we are talking about charging time, so charging time, since it wanted to achieve the plus V saturation value. Okay, so the final value what it wanted to achieve was plus V sat. So we have V final as plus V saturation, and what is V initial? Initial voltage, that is I think minus beta V sat. This is, see, this is minus beta V sat. Fine. Now what is VC? It is only able to achieve till beta V sat, because see again the graph. So it is going till this value plus beta V sat. So it is going from minus beta V sat till beta plus beta V sat, but it wanted to achieve plus V saturation. So finally we have again these three values, and we can get TCS same as TDS RC upon ln 1 minus 1 plus beta upon 1 minus beta. So if we add both to TC and TD, so we will get T equals to 2 RC ln 1 plus beta 1 minus beta. Okay, so beta, what is beta here? R2 upon R2 by R2 plus R3. Okay, so this beta can change according to your feedback network. So I think yeah, I may have some extra question for this also, where the beta value is changing. So we'll see if possible. Okay, so this was the total time taken for charging and discharging. Now, so this is fine. So now we'll talk about monostable multivibrator. So next topic we are moving towards is monostable multivibrator. So we saw that in Astable Multivibrator, we are getting two astable states. So the output is not stable at either of the states. Either it is high then low, high and low. So it is keep on changing. So that are good for clocks and all. So but now we will also see monostable multivibrators. So as the name suggests, it is having only one stable state. Okay, and a quasi state. Quasi means unstable state, or we can say temporary state. So in this monostable multivibrator, it will remain in stable state, until until we apply a trigger. So the statement is saying, so until and unless we apply a trigger to this op amp, it will remain in a stable state. So how it will happen? We just if I illustrate this for you, then let's say this was the stable state for the op amp, high stage. It is there. It is in high state by default. And now if we somehow provide one trigger, let's say a square impulse of very short duration, then what will happen? This voltage will become low. Okay, and after automatically after being for low at low state, automatically it will come again to the high state. So here what we saw, we just applied a trigger for one time, then The op amp changes stage to high to low, then automatically it changes from low to high after some time. So yeah, so this is how this monostable multivibrator operation looks like. So we'll see if we talk about its charging, and again its charging and discharging time for this circuit is depend on the capacitor used. Charging and discharging depends on capacitor used, C used. Okay, and this width which we are achieving here, this width, let's say W width, this is being, this depends on the external circuitry, or we can say the values of resistances and capacitances, the values of resistance and capacitance which you are providing externally to this monostable multivibrator. So this width is based on that. Okay, we'll see how it is based on that. And then application, if we talk about, so these are being used in timers, delay circuits. Okay, then gated circuits also, and frequency dividers. Okay, so it is having many more applications also, but we'll look into the working of this uh, monostable multivibrator. So working. So now how it is working. First of all, we'll see the circuit of this thing. So how this circuit looks like. So we had one op amp, and as we know, we were using the part of a Smith trigger. So Smith trigger is important topic. So we should know about that. So because this topic is being used in every other uh, op amp application, right? So this is the part of Smith trigger which we are using here. Again, the positive feedback circuit. R2, this is R1, this is V naught. Okay, and we had this capacitor also in our stable multivibrator, and one resistor also. So till now the circuit is same. Okay, but what changes here, we just attach one diode here. So this diode will help this circuit remain in particular stable state. So because of this diode, we are making this op amp output to stay in a particular output state. So now what we have to apply trigger also. From here we will apply the trigger. Okay. Hmm. So now after looking at the circuit, we'll see the working of this. So how this will work. So as we know, it is having two states. One is state, permanent state. Another one is temporary state. Okay, so temporary state. So this permanent state can be converted to temporary state. How? Via trigger. We'll see how it will convert. Also, the one more important thing in this is output frequency of this circuit will depend the frequency of the triggers on the frequency of input triggers used. Okay, so now we need only one type. So since we are applying a trigger, so we need only one type of trigger. Either it can be positive or negative. We don't need both the triggers. So in this working, we'll see the working of the circuit using negative triggers. So how it will behave in negative triggering. Okay, so now will I will simultaneously make the this waveforms also for understanding. Okay, so we'll see. So this is triggering pulse. This one we give, again one we give, again one we give. So here these are triggering pulses. Triggering pulses. Okay. Hmm. So since this is negative triggering, so we will see some changes when the trigger is at negative, which is when it is transitioning from high to low. Okay, and yeah, so then we have capacitor voltage and we have op amp voltage. Okay, so now again we are assuming something initially. Let's say initially what is happening, V naught is, we are saying output of the op amp is plus Vsat. Okay, so then the output of the op amp is plus Vsat, and we are assuming this is Vb, this is Vb, and this is Va. Okay, so this is this non-inverting side voltage is Vb, non inverting terminal side voltage of the op amp is Va. So we are saying because V naught is plus Vsat, it is plus Vsat. So we are having beta, we are having what voltage here? Because of positive feedback, beta Vsat. So Vb equals to plus beta Vsat. Fine. So what will happen since this V naught is plus beta Vsat? So it will feed back to this diode and capacitor via this negative feedback. Huh. So what will happen? This diode will be re- forward biased because this side is being this side is looking at the positive side of the voltage, and this is at the negative, that is ground. So this side is at the higher potential. So diode will be in forward bias. Okay. So that is, if this is forward bias, then how it will act? It will act like a DC power supply. That is 0.7 volts. For timing, we are using 0.7 volts here. So this 0.7 volt will be seen by the capacitor across the capacitor. So VC voltage, that is the capacitor voltage, it will be 0.7 volts. And this capacitor voltage is same as that VA. That is the voltage at the inverting side of the op amp. Okay. So VA here I can write also. This is equals to VC. Fine. So this VC will be equal to VA. So now, so we will have, so initially once the trigger is not applied, initially when the trigger is not applied, the voltage across VC is VD, that is equals to 0.7 volts. Okay, and the output voltage is plus V, this is beta plus Vset plus V saturation. So now this is all happening before the trigger. So now what will happen, just when we apply this trigger, negative trigger, what will happen? So before that, VA, yeah. So this VA is less than VB. VB is what? Equals to beta Vsat. We discuss here. Okay. So this is beta Vsat, which is normally higher than 0.7 volts. So VB is greater than VA. That's why we are having plus Vsat. So then, uh, when we applied, when we apply positive, when we apply negative trigger, when we apply negative trigger here. Okay. So then at VB. So what when so momentarily we applied this negative trigger in this VB. So what will happen? So this VB voltage is negative. So momentarily this VB voltage will be more than, it will be like the VA voltage. So we are saying this VA voltage will be more than VB because we are applying a negative trigger at the VB side, at the non-inverting side of the op amp. So because of that, what is happening? This voltage VB is becoming less than the VA voltage. So momentarily This is happening like VA is greater than VB. Okay, so because of that, the output of the op amp, see output of op amp will be equals to minus V saturation. It will just flip the they flip the output of the op amp because VA is now greater than VB. So it will be like this. Okay, this is negative V set. Fine. Then, since the output of the op amp is now changed from plus V set to minus V set, so the positive the voltage through the positive feedback, it will become, this will become, this voltage VB will become minus, VB will be equal to minus beta V saturation. Okay, till now I think it is fine. So what we are doing, we are initially saying that the output voltage of the op amp is plus V sat. Because of that, the voltage being fed back from the positive feedback is plus beta V sat. Then the diode becomes forward biased because this diode is seeing the positive voltage through the negative side of the op amp, negative feedback side of the op amp. Then VC is zero point 0.7 volt because diode is across the capacitor. That is equals to VA. That is the inverting side of the op amp. So this VA is less than VB because VB is B plus beta V sat. Now what will happen when we apply a negative trigger at VB? So this VA will momentarily will be higher than VB because we are applying a negative trigger at the VB voltage. So then because of that, the output of the op amp will become minus V sat, minus V sat. Because of that, then VB equals to minus beta V sat because this is the voltage being fed back from the positive feedback. Now what will happen? The diode we were looking at, that will become reverse biased. That is obvious. So this diode will become reverse biased. Okay, this will be reverse biased. Then the capacitor was having zero point 0.7 volt across it. The capacitor will start discharging. Will, or we can say the capacitor will start charging towards minus V set value. That is through R resistance. R resistance is in the negative feedback. This R resistance. Through this, it will start charging till minus V set. So this the VC voltage will start discharging, or we can say, so it will be like this. Okay, so it will go until it reaches what, minus beta V set value. So this op amp is maintaining a minus at VB, it is maintaining minus beta V set value. So this the voltage of the capacitor will keep on reducing because of this minus V set. So it will keep on decreasing. Once it reaches below this VB value, what will happen again? VB will be more than VA. So huh. So then what will happen? When VB will be more than VA at this point, okay, at this point, then then output becomes plus V saturation. Okay, the output become plus V saturation, and again the diode will become forward bias. That is, again the cycle is repeating. So this will be the voltage across op amp will be again high V naught, and this the capacitance voltage, it will then charge till it will charge till this diode zero point 0.7 volts, and then it will become 0.7 volt, the continuous volt, it will maintain a constant voltage across the capacitor. So this charging time is very less because we are assuming this RC is very less than we are assuming RC is very greater than R1 C1. Yeah, the this RC, the time constant, or we can say it is not this RC basically. Yeah. The diode, the charging from the diode via the diode, this via the diode, when the diode is open, the time constant of this circuit is very high or very low. Sorry, RC is very low now. Yeah, RC is, sorry, the time constant is very high. That's why it will like charge like it will charge instantaneously. So here it will charge and then it will maintain 0.7 volts. Okay. So then again, if you use a trigger here, so then again it will discharge. Then again it will charge like this. Then again it will discharge. Again it will charge like this, and we'll see this voltage here. So here the change in the state of the output of the op amp is being controlled by the trigger being applied at the non-inverting side of the op amp. Now we will look how the again we will see the how we will achieve the total time charging and discharging time of this op amp, as we know this charging and discharging time is given by 2 RC ln 1 upon 1 minus beta. Okay. Now this charging, for one important thing, this charging time is for the ideal diode. Here we are not considering the practical diode case. Okay, so we'll derive how this we can see how we can derive this thing. So again we'll use that formula Vc of t equals to v final plus v initial minus v final e to the power minus t by rc. Okay, so now if we talk about the charging, discharging, this point td, discharging point. So initially it is since if it is a no, ideal diode, then this VD is not 0.7 volt, it is 0 volts. And so we'll see. So the initial stages, we say V initial will be 0 volts, because we are talking about ideal case of diode. Okay, and V final will be what it wants to achieve, minus V saturation value, but it will unable to do that. It will be unable to do that. So V final will be minus V sat, and the VC at T, or we can say TD, discharging till discharging point, here till this point, it will be VCT of D will be what, minus beta V sat, minus beta V saturation. So if we use this in this formula, minus beta V saturation equals to minus V saturation plus V saturation e to the minus t1 by rc, that is td. So we will solve this, we'll get td equals to what, t equals to rc ln 1 plus r1 by r2, or we can say rc ln 1 upon 1 minus beta. Here beta is what we saw, here beta is what, r1 upon r1 upon r1 plus r2. So beta is 1 upon r1 plus r2. This is beta value. Okay. So this we got TD. Similarly, we have TC equals to same RC ln 1 upon 1 minus beta. So that's why based on this total time we got as 2 RC ln 1 upon 1 minus beta. Okay. This is for ideal diode. Ideal diode. This is ideal diode. Fine. So yeah. So what else? This for this. So now yeah, one more thing. I'll add some pages in this. Okay, so now we saw that we are applying a trigger in that the non-inverting side of the op amp, but how this trigger is being generated, that is also important. So this trigger we can generate using a RC network. That is how, if we give one, how to generate trigger, how to generate trigger, trigger pulse, or we can say. Okay, so if we give a square wave in this circuit, what will happen? This is C, this is R. So the output will be trigger pulses like this, and it will be like this. So, but since we were talking about negative trigger op amp, so instead of this, we can use one diode here, that is like this. So only it will pass the negative trigger pulses, and it will not pass, it will block the positive pulses. So we'll get, using this circuit, we'll get this like this. The output will be like this, and this is being fed to the non-inverting side of the op amp. So the final circuit, it will look like this. For the monostable multivibrator, it will look like this. We have this op amp plus, this is minus, we have one resistor here, we have one capacitor here, we have one diode. Okay, then we have the positive feedback network R2 by R1. This is V naught. Okay, this is the trigger circuit. We are just using the trigger circuit here. Fine. This is C, R, D, this is D1, this is D2, this is the square impulse, like this we can give. Okay, V input. So it will allow only the positive trigger, and based on that we can achieve the monostable multivibrator uh, characteristics from this circuit. Fine. Hmm. So till now we talked about lots of non-linear applications of op amp, like Smith trigger, comparators, window detectors, and then we talked about this what we say, uh, this monostable multivibrators, astable multivibrators. So these all are really important. Like we saw the applications also of these circuits, and now after that, after going through these non-linear applications, we'll see another lecture. Another topic of this lecture was voltage controlled current source. So basically, if we can control the current using the voltage, just varying the voltage, so can we achieve that thing using op amps? So can we do that? So that also we can achieve, and we can achieve quite stable current sources based on that, which are, and we can achieve many more current sources which are um, which have very less effect of the load circuit, that is, which is having very less effect of loading on them using the op amps. So how we can do that? So first of all, we have bipolar current circuits all in this, and unipolar. As the name suggests, bipolar is the current source which can send current in both directions. Current can be sent in both directions. Okay, and this current can be sent in one direction only. Okay, this is one thing. Now we saw the one application, one, or we can say uh, what happened? Yeah. Uh, yeah. So we saw one application of high current applications, like when we give for high current applications. So voltage current source for high current application. So we saw that if we have a control signal from here, we input, we are giving 2 add voltage divider, then this is being fed to this is negative. Now we are talking about the negative feedback circuit. Now non-linearity is not there. Earlier we were talking about the non-linear circuits, where we were giving a positive, we were using the positive feedback circuit for this op amp, but now we are only using the negative feedback circuit. That is, now we are not dealing with the non-linearities of the op amps. So here, if we can attach one BJT here, this is R1, this is ground, and we have our load resistor, load impedance circuit. This is I out. So this is the output current, and this is being controlled by this V input, as whatever the V input signal, whatever the signal it will be here, V1, it will achieve, we will get it here, we using the concept of virtual short. And this V1, the current here, it will be I out will be approximately equal to V1 by R1, if we consider the base current of this BJT is very less. Hmm. So we can see that this op amp is driving this BJT into active region, where this is forward bias, this portion, and this portion is reverse bias. Okay, this circuit is in active region, BJT. Based on that, we are getting our I output equals to V1 by R1. Okay, so this is how high currents we can achieve. So if we keep R1 equals to 1 ohm, but at the same time the power should be high, that is 10 watt. The power rating of the resistor should be high, and we saw that in the experiments also, that we use a 10 watt resistor, that was of green color, that was very big in size. So there, here we got R1 equals to 1 ohm, 10 watt, and using this we can achieve even, so we solved one question also where we achieved a current of, I think, 3.2 ampere. That is very high current, very high current. Okay, so this we achieved. So yeah, so this is how we achieve P equals to I square R. So based on that, we achieve this current, 3.2 ampere. So this circuit can be used for high current applications, and we can also improve the performance of this circuit using this BJT. In like, instead of using BJT, we can use MOSFETs and all, in which, like, the effect of the loading will not be there, and the, or we can say basically the base current will be almost zero. Okay, so it is there. And then we saw different configurations of voltage to current converter, but for less values, but for like less range of current. So one was, I'll draw it for you. One, we saw this. So here we are having R, this is also R. This is the load resistance RL, across which we are getting the I output current, I out. This is R, this is V input. So once we are applying this V in, based on that we are changing this I out. Okay, this is I2, this is I1. Okay, so here this is grounded load. Why we are saying grounded load? Because our load is grounded. Okay, our load is grounded here. And we saw also the, like, floating load with non-inverting configurations, as like we had uh, one op amp, then so here it was being connected at the output, V output, this ZL, this is the load, this is the load, this is V input, and this was floating load. Okay, floating load, because it's one side is floating, that is V naught. And this was non-inverting configuration, because the input is at non-inverting side. Again, we can have an inverting configuration also, where the input is at inverting side of the op amp. So these were the voltage controlled current sources. And then as I talked about, we saw one experiment also where we achieved this value of current 3.2 amperes, not 3.2 amperes, less than that, I think. Yeah. So based on changing the V input, so we achieved that thing. So this was an overview of what we studied in this lectures, week 5 lectures. Now we'll discuss about the assignment questions. So I have the, yeah, PDF for that. So before that, if you have any doubts, you can ask. We'll also solve some extra questions today, which are like which we'll see, like there's a good uh, we'll see the application aspect of these op amps, the non-linear op amps like mono mono multivibrators, monostable multivibrators, and other things. So we'll see after we'll discuss this assignment questions. So yeah, we'll go one by one. So the first question, I'll just give you again the hints for this question. I'll not solve, I'll not give the answer. So like the first question say that which one of the following circuit is used for converting a sine wave into a square wave. So this we have done already, like uh, maybe not in this week, not in this week 5, maybe earlier week also. So we can say as more bistable multivibrator, what was the output, and bistable was like this. Okay, but since this output was being achieved by what input wave, we can say that as we know. But we know one thing, that in our stable multivibrators, uh, we don't even need this thing, like any input also. Okay, as we saw here, I'll just show you. Yeah. So this circuit was like capacitor and resistance, and then Smith trigger was there in that. So we were getting this both positive and negative, like high and low voltages, low output voltages. So here and in Smith trigger, we saw how we can actually control the output waveform in monostable multivibrator. I think my bistable multivibrator, or we can say monostable multivibrator. We saw that how we can generate the output waveform based on the triggers being applied from our side. That triggers are in control of our side. So based on that, you can simply say why how the sine wave can be converted into a square wave. This question. Then the next question is a 1 millisecond pulse can be stretched to 1 second pulse by using. So basically, we are giving some pulse. So we are giving some pulse that is very short in duration. That is only 1 millisecond. So based on that, can be achieved a pulse which is 1 second in duration. So I think this we just now we studied this thing about this thing, and you can, I think, answer about this. So like how we can do this. That is also easy. Nothing to explain in that basically. So next question is, bistable multivator has single stable state, whereas astable multivator has no stable state. So you can answer this question by uh, finding the meanings of these two terms. Okay, these two terms are important. Based on that, you can easily answer this question. Then the fourth question is, in an op amp circuit, when one input terminal of the op amp is grounded and the other terminal becomes a virtual ground. Sorry, can you explain question? Okay, yeah. Wait. So yeah, so it is saying a 1 millisecond pulse can be stretched to 1 second pulse by using. So they are saying we are giving from our side, we are giving a very short duration pulse. So can we stretch that pulse like into the like more of a pulse we're having more width, like this is 1 second pulse. So if you will see in this like okay, I will give you more hints in this. So we saw this monostable multivibrator. Okay, so what we saw in that, so we saw we are giving trigger to that circuit. I'll just see, I'll show you. So here, see this. Uh, I gave a trigger to this side. So if you see the waveform of this circuit, I gave a simple trigger. So this is what duration, very less duration. But based on that, this op amp was being driven into negative stage, but the the duration of this pulse was high. It is obviously it was higher than this short duration pulse, that is the trigger pulse. So what it is doing, it is basically the input signal which we are giving, that is the trigger signal, that is like that is very small here. It is very small. Okay, it is being, see, it is being stretched to a more to a pulse which is having more width. So see, base. So this happened. Why this happened? This happened because we gave the trigger. If we wouldn't have given the trigger, then it would have remained in this plus VSAT only, VSAT position. Okay, just because we gave the trigger, that's why it was being driven into minus VSAT in, and it kept for minus, and it was being there in that minus VSAT position for some time. Then it came back to its original state, that is the stable state, that is plus VSAT. So what we observed here, using a very small bit trigger, we were able to stretch the output. Okay, we were able to stretch the output waveform. So this is what the question is asking from you. So I think it is clear. Is it clear, Madhvi? Okay, thank you. So yeah, so coming back to the fourth question, in an op-amp circuit, when one input terminal of the op-amp is grounded, the other terminal becomes a virtual ground. So this is one thing. So we are saying in an open circuit, when one input terminal, so they are saying one input terminal is grounded, of the op-amp is grounded, the other terminal becomes a virtual ground. So this is plus, this is, so they are saying this becomes 0 volts. Okay, this happens. We know this happens. So that means this statement is at least true. Okay, in an op amp, when one in VR. Then the reason they are saying the gain of the op amp is very high. So is this reason correct or not? So how we'll see that? So if this is one thing, this reason is itself in individuality, it is true that the gain of the op amp is very high. We know that the open loop gain of the op amp is very high. That is true. But is it the correct reason for this thing? Is that the thing? So to look into that thing, how we can solve this? So we see V naught, what we know. The V naught is, if we say this is V1, let's forget about this V1 and V2. Let's forget about this. We are just analyzing by giving one V1 voltage here and V2 voltage here to this op amp, and we have, so it is the output of the op amp is given by what? V naught equals to VDA. Okay, this is VDA. So now if we talk about this, VD is what? V1, or we can say V2 minus V1. This is A. This is V naught. Fine. So now if we can move this A to this side, V naught by A equals to V2 minus V1. So now in this case, if this A, we are talking about the open loop gain. So this is open loop. We haven't like given any negative feedback till now. Till now we haven't given any negative feedback. We are just analyzing. So this open loop gain, let's clear it. So if this is tends to infinity, so what will happen? If this A tends to infinity, that is, it is having very high gain. What will happen? This whole value will tends to 0. Okay, then what will happen? This will become V, that will implies V2 equals to V1. Okay, because this becomes 0, this thing becomes 0, so so this equation will become V2 equals to V1. So that we can say, if the op amp is having very high gain, the open loop gain of the op amp is very high, so the virtual short concept we can see in that op amp. So that's why when we look into the characteristics, when we look into the data sheet of the op amp, we see these things. I'll show you here. We see one gain here, it is in dB. Normally it is given in dB and frequency plot. So it is like this. See, we see this gain like this. Okay, so this is like when we are talking about, let's say, f cutoff. So this gain is very high, 90 dB or like 110 dB. So why people say we should not use the op amp let's say this is the gain bandwidth product where the op amp gain is 1 or the dB is 0. Okay, why people say don't use the op amp beyond its gain bandwidth product? The gain will become less than 1 or the 0 dB, or it will become, the gain will decrease. So if the open loop gain will decrease, so the op amp will be able to see the effect of, will not be able to see the effect of virtual ground or virtual short in this op amp, because it is moving away from its ideal behavior. So ideal behavior it can achieve here when the gain is very high, like 90 dB, or we can say 110 dB. There the open loop gain is very high. So since the open loop gain is very high, we are getting virtual short here. But since if we'll use frequency at very high value, then we cannot see the virtual short here. Okay, so that's why these things you should keep in mind. So I think this question is clear. So this statement is true, this is true, the gain of the op amp is very high. Yes, it is high, and it is also the right explanation for the assertion, the above statement. Fine. So okay, I gave the answer for this question 4. Anyway, question 5, yeah. This is also a simple question. What is the value of R4 in the given circuit if the voltage V minus and V plus are to be amplified by the same amplification factor? So they are simply saying this V minus and V plus voltages should be amplified using the same amplification factor. So basically, whenever you see circuit like this, just go for KCL and KVL equations and get a relation of this input voltages in terms of V output voltages. Okay, so how we'll see that? So we can say this is VA voltage. Since this is a negative feedback, we can say this is also VA. First of all, identify whether it is a negative feedback circuit or positive feedback circuit. Like either it is in non-linear, it is behaving like a non-linear circuit, or as a proper ideal linear circuit. So here, since it is negative feedback, we know that this will be working in negative feedback in linear. It will be showing linear characteristics. So that's why we show that it can have virtual short characteristics. Okay, another thing. Now what will happen? So what VA will be? So this is a potential divider circuit. So VA will be V plus into R4 upon R4 plus R3. Fine. This VA will be transferred here because of virtual short. Then if we use KCL here in this node, VA node, so we will get VA minus V minus divided by R1 plus VA minus V naught divided by R2 equals to 0. So if we'll solve this, so what we will get, we'll get some equation in terms of V plus. We will be having something here. We'll also get V minus in terms of equation like here, like this, where we'll be having some coefficients of V plus and V minus basically, and this will be V naught. So whatever the coefficients will be, so the question is saying the amplification factor should be same. That means these are the amplification factor. The coefficients of V plus and V minus in the final equations will be the amplification factor. That is how they are being amplified to get this output voltage. So these should be made equal. That's how you will achieve the answer for this question. That's all. Okay. So based on that, you will get the resistance values in this question. This is easy. Okay, fifth part. Okay. Then sixth question. A triangular square wave generator uses. So basically, if you are saying triangular square wave generator, so we are saying about a square wave generator and a triangular generator. So how it can be achieved? So if we will, let's say we'll integrate this thing. Uh, if we'll integrate this thing, what we'll get? We'll get a triangular wave, no? So, and we know why we use comparators and all those things. We use comparators and all to shape the circuits. So can we use? So you will have to think like this. This thing can be integrated into a triangular waveform. One thing, and yeah. So and another, like just see whether sine wave can be integrated or differentiated to get a triangular. No, we can never get that. If we'll integrate this, we'll get we'll get another sinusoidal or we'll differentiate it, and again we'll get the sinusoidal wave. So we cannot use a sine wave at least. So that is the very clear cut clear cut thing which is there. So we can get triangular square wave. So these options can be we can uh, cut those options. So we are left with these two options. So since we are generating triangular waveform from the square wave generator, so that's why based on that you can answer this question. Okay. So this is I think fine. Now seventh question: a three-terminal monolithic IC regulator can be used as. So they are saying how this can be used as a three-terminal monolithic IC regulator. So I think this there is some anomaly. One person also asked doubt about this. So that was in discussion forum. So I'm clear. So what I checked. So I think the answer is maybe it is wrong, and because I checked one three terminal monolithic IC, so that was I think LM317. Yeah, so that is adjustable regulator, that is LM317 IC. So we have it is like this. See, so here in their data sheet they are saying since it can be used as voltage regulator, that is one thing. Another thing what I saw, that it can also be used as, just show you the thing. Mm, yeah, it was somewhere in the description that it was written. Yeah, I think here somewhere here. Huh. Yeah. So yeah. So yeah, they are saying the LM317 device can function as a precision current regulator also. So and in the options it is although the answer is wrong, it can be used as voltage regulator and as well as current regulator also. So that was one thing. I will have to see. Yeah, but I think the answer is wrong. So here was one anomaly in this question. So yeah, moving to the next question. Which one of the following is an example of a regulated power supply? You can simply go through the data sheets of these ICs and you can check. I think this is the timer IC. That is IC triple five, and I have the simply you can go with the data sheet and you can check uh, which is having the which can be used as regulated power supply. So that is also easy, very easy. Which one of the following statement is true? Monostable multivibrator can be used to alter the pulse width of the repeated pulse chain. Monostable multivibrator has double stable state. So based on the features and the facts given to you, provided to you, so you can answer this question also. That is also easy. Okay. Now this question, yeah, as shown in the figure, the current flowing through the resistance of 100 ohm would be. So it is also again simple. First of all, we'll see whether this BJT is working in active region or like which region. So if we are providing 2 volts here, and this is yeah, I think okay, this is so this is since this is 2 volts, so based on the virtual short we can say this is also 2 volts. Okay, so this will be 2 volts. So we can find the current here, that is 10 minus 2 by 1k. We'll get the current 8 milli. And if this is almost the if we are neglecting bias current or the base current in this BJT, then we can get the current through this 100 ohm resistor. Okay, that is another thing. Then yeah, this is all about the assignment questions. Any doubts in these questions? This 10 question also easy, ninth easy, eighth also, seventh. After this, we'll solve some extra questions that are good questions. So before that, moving towards that, if any other doubts, sixth question, fifth question, fourth. If you want me to explain any question again, then also you can comment in this chat box. If no, then we'll move towards some extra questions. These are really good questions. So two questions were from uh, the previous class. Like why I was unable to solve that because of the time. But yeah, here we will see that question. So this question is basically okay. No sir. Okay, thanks. Yeah. So first question. Now we'll talk about extra questions. Extra questions. So this will give you a good insight about okay how these non-linear op-amp circuits can be applied. So here is this. Okay, yeah. So yeah, for the one for the for the people who joined just now, so for them, just again I'm saying that now I'm discussing about the extra questions, which can be like which can give good intuitive feeling about okay what how this application how the op-amps can be applied in various fields. Okay, so the first question, just look into that. Show that the question is saying we have a window detector in front of us. That is this figure as a window center is controlled by V1. Okay, that is V1 is this one, and whose width is controlled by V2. Okay, that they are saying this. Then sketch and label the VTC, the voltage transfer characteristics. If V1 is 3 volts and V2 is 1 volts, so they are saying like this. So how will solve this? First, analyze this circuit. Although it looks little complicated, but it is not. If you will analyze, so if you see Vi voltage we are giving here, and it is being fed to this op amp also. This is op amp. We will say let's say this is op amp 1, this is op amp A2. Fine. So we'll say this as Va minus. This is will I'm just using this Va plus A1. Okay, this is Va plus A2. This one will be Va2 minus. Fine. So this voltage I just named these voltages, the voltage at the terminal of these op amps. Fine. So we will go one by one. Okay. We know that this is a window detector. They have made it clear since they have no feedback circuit, anything, nothing like that. So we can say okay, these are working as a comparator. Simple. So that's why these are two window detectors. Only one thing in class we studied about two inputs. Now we have one more input in this. So how this input, one more input, how this input will be affecting the output of this window detector. We'll see. Okay. So what will be VA1 minus what it will be this Va1 minus. So we know Vi is being applied to this, and this is grounded. So we have these two resistance only. So this the voltage is here. So it can be easily said that uh, this will be Vi by we'll say by 2. Okay, so these are both same resistors R, and these are R and R. Okay, so the voltage is being divided equally between them. So we are talking about this branch. So here the Va1 minus will be Vi by 2. Similarly, what will be Va1 plus? Not similarly, what will be Va1 plus? So I will just remove this for like easy understanding. Yeah. So what will be Va1 plus? So here we'll have to just if we can see if for you I will just separately will draw the circuit for this Va1 plus. So this is op amp plus, this is minus. I'm talking about A1 op amp. So this is the this line, this terminal. Fine. So we have from V1. So okay. So what? So V1 is being attached to this. So we can see from here when V1 is attached. So we'll say okay. V1 is attached here. V1 here is one resistor R. So V1 is attached. One resistor is there. Then it is being fed to this one point. Another terminal is given from here. This is R, and this being fed till here. Then V2 is being fed from this point. Okay, this is V2 point. So V2, we'll see this is what we'll say another resistor. Sorry, not here, from here. This is another resistor. This is being V2 being fed from here. Okay. Till now it is, I think, fine. uh, just I will clearly I will make this circuit. This is R. So we have at this terminal, we are looking a circuit something like this. So how will solve this? You can solve this using simple voltage transformation, voltage to current transformation. If you really, or we like, yeah, we can simply, what we can say, just for the sake of simplicity, this R and R is parallel, R parallel R, and this is this voltage. This will be converted to current sources. See, this will be V1 by R, this will be V2 by R. Okay, this is the input side of the op amp, and this will be what, V1 plus V2 by R, the total current source. Okay, this is total current being fed from here, and this is the parallel resistance R, that is R by 2, basically R by 2. So the equivalent circuit of this will be what? We'll get one R by 2 circuit here, and we'll get the voltage will get is V1 plus V2 by 2 into R, yeah, divide by R by 2, R by 2. So 2 will get cancelled, this will get V1 plus V2 by 2. So basically we are applying V1 plus V2, V1 plus V2 by 2 input at this op amp. Okay, so what will be VA1 plus, that is the voltage at this terminal, that will be V1 plus V2 by 2. Fine, this much is okay. Again signal lost. Okay. I think signal is lost. इसकी बैटरी डाउन हो गई थी तो कनेक्ट कर हॉटस्पॉट से कनेक्ट कर दो. Uh, okay. Yeah, sorry for that. Again, that some net issue happened. I'm connecting it again. Wait, just wait. Yeah, yeah, yeah. Some net issue happened. Wait, just wait. Oh, Yeah, sorry for that. Some issue is there. Yeah, some network issue is there. Yeah, just coming back. Wait, wait, wait. So yeah, I was wait, go and present share screen. Hmm. Yeah. Sorry for that. So yeah, we were till here. V1 plus V2 by 2. Okay. So yeah, some network issues may happen. So sorry for that. Uh, yeah. So okay. So VA1 plus we got V1 plus V2 by 2 by solving this volt the V like converting this voltage source into current and then converting back into the voltage source. We got this VA1 plus voltage. Okay, so we got VA1 this one voltage and VA1 plus voltage also. So now we also have VA2 plus and VA2 minus voltages also. So how we'll get? So it is also simple. So VA2 minus VA2 minus will be what? That is the voltage across this the negative, the inverting side of this op amp A2. Okay, so it will be what? So this is being fed from this V1, this voltage. I'll just clear the other things. Okay, I'll just clear for clarity. This is V plus. Yeah. So this is so we are talking about this one VA2 minus. So this voltage is being fed from this V1 voltage that is being fed from here. So again we have two resistances, so it will be divided by 2. So it will be V1 by 2. Fine. And what will be VA2 plus voltage? It is again the same concept as we applied in this VA1 plus voltage. That same concept we can apply at VA2 plus voltage. But here we have one V2 voltage that is being connected through here, and we have another voltage that is connected from VI. Okay, so we will have VA2 plus equals to V2 plus VI by 2. So I'm just writing all the equations here. VA1 minus, that will be, that is what, VI by 2, that is VI by 2, and VA2 plus, okay, that is V1 plus V2 by 2. This is what we got. So these are the four voltages at the input terminals of these two comparators. Now now the question is saying that we have to achieve a bit which is controlled by V2. So whose center is controlled by V1? We have to show that this window detector, the center of this is being controlled by the V1 voltage. So how will show that? So we know that one thing, the output. Let's say, let's assume that the V output is V saturation. The window detector output here, that is this V naught, is V saturation. That is at the high voltage, at the high stage. V saturation. So what will happen in this case? How it will be? When it will happen? Like it will happen when VA1 plus is greater than VA1 minus and VA2 plus is greater than VA2 minus. So what I will write it here. So we have the comparator like this. Two comparators we have, minus plus. This we have plus minus. This is A2. This is A1. So this voltage is VA1 minus. This is VA2 plus. This is VA1. This is VA2 plus. This is VA2 minus. Okay. These are the input voltage at these two. This V, then we have V naught. Basically, it is looking like this. So when we'll have V naught as positive saturation, it will be when VA1 plus. That is, this VA1 plus will be higher than VA minus 1. This is fine. This is clear. And for this comparator, it will be when VA2 plus. This VA2 plus, the non-inverting side of the terminal is higher than the VA2 minus. Okay, this is also clear. So in that stage, if we just use these formulas from these four equations, as we derive from these four equations, so we'll get v1 plus v2 by 2 will be greater than vi by 2. We are just substituting these values, these four values from the above equation which we just derived, and vi plus v2 by 2 greater than v1 by 2. Okay, I'll just add one page here. Get page, add one. Landscape. So yeah, okay. So this is there. Now when we have V naught equals to minus V saturation, what will happen? These conditions will be reversed. So VA1 minus will be yeah, it will be greater than VA1 plus, and VA2 minus will be greater than VA2 plus. Okay, this will be there. Then again substituting these values, VI will be greater than V1 plus V2, and V1 will be greater than Vi plus V2. So we got these conditions, and we got this, we can cancel it out. We got these conditions also. So based on these conditions, what we can get from first two conditions, what we can get? We can get Vi by solving these two conditions and simply using the inequalities. Vi is greater than V1 minus V2, but it is less than V1 plus V2. Okay, one condition we got from this point. Another is what? And from this we got Vi is greater than V1 plus V2, that, and this is V1 minus V2. So this condition. So this is the condition. So first of all, this condition is when V naught is minus V saturation. This condition is when V naught is plus V saturation. Okay. So we have these two. So now how will plot the VTC? We have V naught here. Okay, and the, let's say V minus V saturation we have like this. Minus V saturation is till when point? What point? V1 plus, when it is get so yeah, so, or we can say this is V1 minus V2 point, this point, this is point V1 plus V2, this is what? Vi, uh sorry, Vi is this, sorry, Vi not this is V1. Okay, this is V1. So we have a high voltage between these two points. So we will get high voltages between like this. Okay, this is plus V saturation. Based on these conditions, we got this. So here at the center of these 2 points is what? V1. We can get that by adding these two values and dividing it by 2. So we can get the center as V1. That is what being asked in the question also. Like we have to say that the V center is controlled by V1. That is we achieved. Okay, and width is controlled by V2. That is what also what we are seeing here. So width is being controlled by V2, and the center is being controlled by V1, and the rest of the part is being decided by this equation. So the rest of the part is minus Vz, like this. Okay, so the values given in the question you can substitute, and accordingly you can get the values of V1 and V1, like the center point and the width of the this window. So that is like based on V1 equals to 3 volt and V2 equals to 1 volt. You can get the width of this window. So basically we got this window. Okay, we got this window, the width of the window which is being decided by this V1 voltage. Sorry, the center of the window is being decided by the V1 voltage, and the width is being decided by the V2 voltages. Okay, so this question was based on window detector. This is done. Fine. Now we'll move towards the next question. That is like, just see this question. We have we have non-ideal diodes VD on, that is point 0.7 volts we have, and we have saturation voltage. They are asking us to draw the voltage transfer characteristics of the inverting Smith triggers. As I told like previous week, I wanted to tell these questions, but I was unable to, so that's why I'm discussing here. So yeah, so just see this question. So yeah, so how we can solve this question? So we can solve this question. Just say, just I will just mark this as V naught A, just for the simplicity. So we'll go step by step. So this is the output voltage, the final output voltage of this whole circuit. So now we can say, if like we'll go first step, if V naught A equals to what, plus V saturation. So we are assuming that it is at the output of this op amp is at V naught, like positive saturation. So when it will happen? So it will, if it will happen, then what will happen? Then D1, the diode D1 and D4 will be off, and D2 and D3 will be on. See, we apply positive voltage here, so this will become on. But since we are applying positive voltage, so D1 will be off here. It will be off. Huh? We are applying positive voltage from here, so this D2 will be on, but this D4 will be off. Okay, so that's why these things came. I'll just remove from here. Okay, so then what? How the circuit will look like? The circuit will look like this. The output of the op amp will look like this. So we'll have the D2 is on, so we'll have like this. This is open. We'll have again this is D3, that is 0.7 volts. This is D2.7 volts. D1 and D4 are off. Okay, and we are getting V0 via 1 kilo ohm resistor. Fine, this is fine. Okay, so now what will be the V naught? Simply we can use, this is 15 volts here, and this is 13.3 k, so we can use KVL here. So we will get 15 minus or yeah, 13.3 k I, that is the I current from here, minus 0.7 equals to what? V naught. Okay, simple KVL from like from this point to this point you are getting. And what will be the I? I will be V naught by 1k. Fine, because I is being then given to this, because it cannot enter like in this in these two stages, and it cannot also, like one path is going into the positive terminal of the op amp. Here also I cannot enter. So I, all the I will go from the 1 kilo ohm resistor. Okay, so 15 minus 13.3 k V naught by 1k minus 0.7 equals to V naught. So when you will solve V naught, you will get 1 volt here. Okay, one thing. So this is the condition when we assume V naught A, the output of the op amp is at plus V saturation. So what will happen when the output will be at negative V saturation? V naught equals to minus V saturation. What will happen at that point? So the diodes which were on, they will get off, and the diodes which were like off, they will get on. So D1 D4, what will happen? D1 equals to D4 will get on, D2 and D3 will get off. So how we will see the circuit? The circuit will look like, yeah, the circuit will be D2 and D3 are, this will, oh sorry, this will be now off. So D3 is off. Okay, so D1 will be on. Okay, this will be uh, okay, this one will be like this, 0.7 volts. Okay, this will be off. This will be off. This will be 0.7 volts. Okay, so yeah, so hmm. So we again, now the op amp output is here. plus minus, and the supply, from supply we are getting minus 15 volts. Here we are having 13.3 kilo ohms. Here again in the circuit you can see that, and we have V output, we have 1 kilo ohm resistance, and we have like this. So again the we can use KVL from here. So yeah, KVL from here again we can get V output equals to what, minus 1 volt. Similarly, as we solve this for the positive plus V set situation. Okay, so then what will happen? If we'll so then if we make the voltage transfer characteristics V naught and V, we'll say V input. So what we are observing, V naught will be 1 volt whenever and yeah, one more thing. So what you will observe in here. So what will be the threshold and what will be the, so you see, if the output of the op amp is plus V saturation, or we can say the input. So whatever the input, if the input is uh, it is this yeah, it is positive, like so when VO will be positive plus V saturation, when this voltage will be less than the V plus voltage. Okay, so how we can how we can make this VTC. So we are getting, see, we are getting 1 volt and we are getting minus 1 volt also. Okay, that is one thing. The output is 1 and minus 1 volt. So when the output is going from plus V saturation to minus V saturation, we are getting, we are getting from one, we are transitioning from 1 volt output to minus 1 volt. So 1 volt to minus 1 volt, so we will get this here. Okay, it will be like this, and here it will be opposite. Why we are saying like this? Because this is what, an inverting Smith figure. So when it is like going less than the lower threshold, it will get high. When it is going higher from the upper threshold, this is lower threshold, then it is low. Okay, that is why, because why it is, because this is inverting Smith figure. It is the input voltage is connected to the negative, the inverting terminal of the op amp. And what will be the threshold, the upper threshold and lower threshold? That is like, how you will see that threshold. Since we know that the transitioning is happening because of, based on this 1 volt and minus 1 volt. Okay, as we see that V naught A, whatever like V naught A we are getting here, so the V naught can only go to 1 volt or minus 1 volt, because see, in both the cases, so it cannot go beyond that. So minus 1 volt is the lower threshold and this upper threshold is the plus 1 volt. That is the upper threshold. Okay, because why? Because when we are transitioning from 1 volt to minus 1 volt, the output of the input, the output of the op amp is changing. Similarly, for when we are transitioning from the minus 1 volt to 1 volt, the same is happening. So based on the connection of the VI in the op amp, we can say uh, from the lower threshold whether it will be, the output will be high or low. That is first thing. Second thing, what will be the threshold limits? Threshold limits will be the voltage which we are, the output voltage which we are achieving, which you are achieving when the circuit is on. So we are having only two conditions here. Okay, one is when D1 and D4 is on, other condition is when D3 and D2 is on. Okay, that is clear. So we have 12 more minutes, so we can solve this question. This is based on monostable multivibrator. Just go through this fastly. I'll just solve this question. I had one more question also, but yeah, we won't be able to solve that. Okay, we'll solve this. So yeah, this question is saying that monostable multivibrator circuit. In the stable state, it is saying V naught equals to L plus VA equals to 0. So they are saying VA equals to 0, VB equals to minus VF. Okay, and the circuit can be triggered by applying a positive input pulse of height greater than VRF. So how you will solve this? So what are the stable state conditions? So stable state conditions are stable state conditions. Okay, conditions. It will be C. Uh, so V naught we know as given in the question stable state condition V naught is high, that is L plus VA equals to 0. It is given VB equals to minus V reference, and one more condition they have given, that is RC is very greater than R1 C1. Okay, so that is implying C will discharge slowly. C will discharge slowly. Okay, fine. So if we'll talk about, so let's say we'll go step by step. If we talk about a trigger, let's say we applied a trigger. Okay, so this is so so this is the square pulse wave which we gave to this input, and it is this is converting this circuit is converting the square wave into a positive trigger like this. Okay, as we saw in the monostable multivibrator. So initially it was V minus reference. This is the stable state. This is the stable state. So VA is 0. So this voltage is VB. That is the trigger voltage. So this is the 0 volt line. So trigger we are applying a little higher than the 0 volts. Okay, yeah. So yeah, again I'm just repeating this question. Just see this. So they are saying that V naught equals to L plus, like these are the stable state conditions. So V output of this op amp is the plus V side condition. VA, this side input is 0 when it is in stable state. They are saying that it is being given in the question. And VB is minus V reference. This VB is minus V reference. Okay. And one more condition is given, C1 R1 is very less than CR. So how we have to like derive this formula. So how we'll do that? So we know that stable state as given in the equation, that is V output is plus V set, that is L plus VA equals to 0. Okay, VB is minus V reference, that is given in the equation, and this also one condition is given. This condition means that C will discharge slowly. Okay, because RC time constant is higher, so that means this RC network will discharge slowly in comparison to this network. Okay, so now let's say we gave a pulse. So this is the stable region. This portion. So we gave a pulse. To this R1 C1 network. So what will happen? It will convert it into a trigger like this. Okay, as we saw in the monostable multivibrator case. Fine. So then, so this VB, that is the VB voltage. The VB voltage is this voltage VB. Initially in the stable state, they are given that it is minus V reference. Okay. So initially it is minus V reference. So here somewhere it is 0 volts. Okay, we are saying the 0 volt line is here. In the stable state it is minus V reference. We have given a square pulse then. So the trigger is like this. It is looking like this. So then now what will be VA? How the VA will be looking like? So VA initially at the stable state it was 0. So let's say in the stable state it is 0 volts. This is 0 volts. Here it is 0. Once we give the trigger, what will happen? So I will just make a circuit for you. So circuit will look like this. See. So we gave a positive trigger here. So what will happen? It will make this VB greater than VA momentarily. Okay, because VA is 0 volts. In stable state, they are saying that VA is 0 volts. So once we give a positive trigger at VB, so this VB voltage will be greater than VA. Based on that, this op amp initially it was at stable state, it was at L plus, that is plus V set. It will move to L minus state because VB becomes higher. Okay, so then this will L from L plus it will move to L minus state. This is V naught. Okay, I am talking about C and this is R. Only I am talking about only this circuit. Okay, and this is VA. Initially it was 0 volts. Now it will move towards, since this is L minus, so it will move towards minus what? We'll see what will the voltage of this circuit. Because initially when it is at stable state, this is 0. this capacitor has been charged till what, L plus voltage, because we are using this condition. Because the current constant of this capacitance is very high, so this capacitance won't be able to discharge when this transitioning will be happening. So then what will happen, this capacitor will be remain at L plus voltage. Okay, this capacitor will remain at L plus voltage then. So but now the transition has happened from L plus to L minus at the output. So what will be the VA voltage? So VA voltage will be VA, we'll use simple KCL here. VA plus L plus equals to L minus. So VA will be L minus minus L plus. Okay, this will be the VA voltage. Fine. This will become VA voltage. So we were talking about VA voltage. This will goes immediately to VL minus L plus voltage. Fine. Then now this VA has become like this. Now this capacitor will start discharging, or we can say start charging. So this capacitance voltage will start changing like this. Once it reaches this minus Vref voltage, okay, this is minus Vref voltage. So this capacitor voltage, once it reaches minus Vref, then what will happen? I'll just add one page. Uh, yeah, add one page. Uh, okay. So yeah, this when it reaches minus Vref, what will happen? So yeah, initially the output at stable state it was L plus the output. This is the output. Okay, initially it was stable. Once this thing happened, it will go. The output will become L minus. Fine. This is the output of the op amp. So initially it was L plus, then it will become L minus. Once it reaches the A VA voltage reaches minus Vref, since the capacitor is like charging again, this capacitor charging again, so it will charge and it will reach to minus Vref. Then what will happen? This voltage will again this minus Vref. So the again this VA will be minus. It will, so this VB is minus Vref now. Okay. This VB. We can say, yeah, this VB is now, yeah, it became minus Vref here. So once it reaches, so the output of the op amp will switch its output. The output of the op amp will switch its position from L minus to L plus now. Because this minus Vref, so this voltage is becoming greater than minus Vref, VA is becoming greater than minus Vref. So it will again switch to high position. So this will again become L plus. So these are the waveforms, and this will again look like this. So this will be L plus minus, or we can minus of L minus e to power minus t by RC. This is the equation of this the charging of this capacitance. That is simply the initial voltage L plus minus of L minus. Here outside it is L minus. That is the initial voltage, which is this, into e to the power minus t by RC. Okay. So this is how this circuit will be looking like. So this is basically this is the unstable region of this op amp. Unstable region of op amp. Okay, where when we applied the trigger, that is what it is looking like. Okay, so based on this equation, we can solve minus what we'll say VA equals to Vref. This is the point where this transition happened. Okay, when VA become equal to Vref, then only this transitioning happening from L minus to L plus of the output voltage. So we say VA equals to Vref, and what will be VA? VA is the this equation. We know this equation is this. That will be this is minus Vref. This that will be L plus minus L minus e to the power minus t by RC. Okay, so t will become RC ln L plus minus L minus divided by Vref. So this is what they were asking for in the question. So yeah, so we solved some questions, extra questions in this session, uh, and we saw the non-linear applications of op-amp. In previous week we saw the comparators and window detectors. In this week we saw, and split triggers also we saw in the previous section, previous week. This week, week 5, that is, we saw astable multivibrators and monostable multivibrators. We saw their applications, their functioning, and how we will derive the charging and discharging time period of these multivibrators. Again, we saw that the monostable multivibrators applications and workings. And then after this, we also saw that how we will generate the trigger pulse in the monostable multivibrator. Okay. Then we saw about the voltage current, control current source, and like in high current application, how they are used with various grounding conditions like grounded load, floating loads. That after that we discuss some assignment questions, and then we discuss some extra questions also. So yeah, thank you for this attending this session. We'll meet in the next session, that is week 6 session of this class. Thank you.